Welcome everybody to discussion hour this week. We're joined by Dr. Tim Urban from UTIG up here on Pickle. And Dr. Urban's areas of expertise include satellite geodesy, remote sensing, orbital mechanics, and mission planning, especially measurement, validation, and AMP calibration. He has worked with several Earth-observing satellite radar and laser altimetry missions and science teams and supports the Reason Radar on Europa Clipper. He is director of NASA's Texas Space Grant Consortium, supporting NASA outreach for the state of Texas with space-focused workforce development programs to inspire students in all STEM fields. And today he'll be talking to us about ICESat-1. Take it away.
Excellent. Well, thank you very much for inviting me here. This is what I did for about a decade and a half before I became director of Texas Space Grant. So for those who just know me as the Space Grant Director, I do some science and engineering as well. ICESat was a really fascinating mission. It was my first mission that I got to be a part of from essentially the beginning to the end. And it's weaved itself through so many of NASA and different space aspects that I put together this presentation that goes pretty far back. And so we're going to talk about space program. Oh, there we go. Back in the beginning. Okay, so we're going to start with World War II. You might have heard of Operation Paperclip. So Werner von Braun and the German scientists were developing the V2 rocket. And when it came down to the end of the war, both the US and Russia wanted those scientists to come to their countries. So on the US side, it was called Operation Paperclip. They gathered Werner von Braun and a lot of his team and moved them to what was called then the White Sands Proving Grounds, which became the White Sands Missile Range. So you'll see on the logo there, it says birthplace of America's missile and space activity. So we're going to come back to White Sands multiple times during this presentation. Just keep that in mind. Next up then came the International Geophysical Year, 1957-58. So that started with Sputnik. Russia got there first. US was still trying to launch a satellite, but they got Sputnik 2 up. That was Laika the dog. Finally, we got a launch attempt, Vanguard, but it blew up on the launch pad. So that was the civilian-based rocket. Eisenhower finally gave permission for use of Werner von Braun's rocket, which had heritage in the V2, which is why he didn't want to use it because it was used for warfare. But it worked. So Explorer 1 was launched January 31st of 58. And then NASA became an entity October 1st, 1958. So now we've got NASA, we can go forward. 61, 62, those were Kennedy's speeches for going to the moon. And that's really where Werner von Braun wanted to go. He wanted to send rockets to the moon. All right, so here's the first concept art of astronauts on the moon. And you can see that they're carrying something here, that little egg crate shaped device. And then when you go to the actual astronauts on the moon, they've actually placed that device. What is it? Anybody know?
The laser reflector.
Yes, you are correct.
More importantly, the seismometer, but.
That too. So lunar laser ranging. This has a huge impact on satellite altimetry and ICESat specifically, but it's a big array of what are called corner cubes. So they have the property where if you look at them, the light is directly back from the direction it was sent. So I'm going to pass these around. These are two corner cubes, and you can see your eyeball staring back at you. All right, so we started lunar laser ranging, which had a huge range of scientific advances. There were actually 5 lunar laser ranging sensors placed on the moon by these different missions. And I think there was a Big Bang Theory episode centered around this as well, trying to prove that the moon landing was real, yes, because we can laser range to it. And a lot of that laser ranging came from right here, McDonald Observatory. So if you've been out there, you might have gotten to see the laser in action. If not, definitely go check it out. And that had a huge impact on verifying plate tectonics and a whole host of other science advances. All right, now we're in the 70s. This is where I come along. So Apollo ran from essentially 68 to 72, plus the 1975 Apollo-Soyuz docking. Viking, that's Carl Sagan there next to the Viking lander, that launched in 74 or 75, launched in 75, landed in 76. Voyager launched in 77. Shuttle started in 77. CSAT, that's the middle bottom picture there, that launched in 78. And then the first funding for Hubble actually was put aside in 1977. So the 70s were huge for these big, giant missions getting started. And we're going to come back to several of them as we go along here. All right, as I said, this is where I come along. That's me in 1973 visiting Kennedy. There. 1976, Viking, I was just captivated by that. And then 1977, something happened that really got me into space. All right, let's talk about shuttle briefly. 30 years of space shuttles. First launched in 1981 with people. It was unmanned. They renamed the Enterprise in 77 and 78. Of course, Columbia and Challenger had accidents, exploded. Enterprise now, I believe, is in a museum in New York. Discovery is at the Smithsonian, Atlantis State in Florida, and Endeavour is at a California Science Museum. So you can go visit all of those if you like. All right, what does the shuttle have to do with ISAT? All right, we don't know yet, but it did launch Hubble. All right, we'll come back to Hubble later. But it launched Hubble in 1990 on STS-82. All right, the shuttle, hey, here's White Sands again. So the primary landing site for the shuttle is Kennedy, the secondary Edwards, and the tertiary landing site is White Sands, New Mexico. So whenever a shuttle was going up or coming down or even in orbit, they were ready there just in case they had to come down. And on the right-hand side, that's a Google Earth map. You can see the X there. That's actually the landing runways right there for the shuttle. All right. During the shuttle era, it only landed at White Sands once. They only did that once, STS-3 in March of 1982. And you got a couple pictures out there. It's a big flat area, a lot of space. That's why they picked it. All right, let's jump to CSAT. Another one of those big 1970s missions. So this was essentially the first big Earth observing mission. It had 5 instruments on board. It had a radar altimeter. It had a SAR. It had 2 radiometers, one for microwave, one for visible and infrared, and a scatterometer. A lot of these were the very first time they were really being tested in space.
It's a visible radiometer, just a instead of camera. This is like a precursor to digital camera.
I guess so, yeah. I mean, it just, yeah, was taking wide swaths of different bands in the visual spectrum, yeah. Early digital camera. It only lasted for a few weeks though. Everything worked great. Some might say too great. So this is a map of the ocean floor that they derived from the CSAT ocean altimetry. You can see some of the ridges and the trenches and things. So it turns out submarines, you want to hide those in trenches. And because the data was not encrypted, anybody could intercept the data. So it suffered a catastrophic electrical failure a few months after launch. So that's the legend. All right, here's a handful of early radar satellites. There was actually one before CSAT called GEOS 3, primarily used by the Navy. It had no onboard storage, so just wherever they could collect data. They had a lot of ships in the North Atlantic collecting the data. That was really early, the first radar altimeter satellite. Then CSAT, Navy had another one called GeoSat. That data was classified until 90s when I was doing my dissertation. I got to look at some of that the first time. And then the first modern radar altimeter, the one that really set the stage for continuity, was Topex Poseidon, launched in 1981. Another thing on Topex that differed from the earlier ones, it had one of these satellite retroreflectors on board, so that we could do laser ranging to the spacecraft and get the orbit very precisely. All right, we're almost to ISAT. There was a workshop in 1988 for the Geodynamics Laser Ranging System, GLRS. So the design at that time was an 18-centimeter telescope, trying to look for tectonic plate motion and ice sheet altimetry. And what they would actually do is put these corner cubes on the ground where they wanted to measure. So they'd have to set these out wherever they wanted to take data. And the spacecraft would shoot the laser down and you get data that way. That was the early concept. All right, meanwhile, Mars already has a laser altimeter up there. MOLA, operated from 97 to 2001. It gave us what people at the time were saying was a better view of Mars than we had of Earth. So people were really pushing to get a laser altimeter on some sort of Earth observing spacecraft. The laser for MOLA was 1064 nanometers infrared. It operated at 10 hertz. So that means the spots were 330 meters apart. And each spot on the ground was about 100 meters in diameter. Because of the orbit precision, the altitude we would get was a precision of about 37 centimeters, and the accuracy was somewhere less than 10 meters. Okay, so before ISAC, before GLASS, they actually put a laser on the shuttle. So the shuttle laser altimeters were put up there in 96 and 97. Again, these were MOLA Heritage, so they operated at 10 hertz, 100 meter diameter. Because the shuttle's going at 7 kilometers a second, that means the spaces were 700 meters apart. And of course, it only operated between the latitudes of the shuttle. So that's that narrow red band of orbit tracks there. All right, finally, we're at ISAT. All right, so this is the Ice Cloud and Land Elevation Satellite. It has one instrument, one alone, called GLASS. Instead of GLRS, they changed it to GLASS. It's the Geoscience Laser Altimeter System. And there's a cool shot from NASA graphics. All right, so the mission goals centered around ice, clouds, and land elevation. So it was designed to measure centimeter per year changes in the polar ice topography. For clouds, it just measured the distribution of clouds and aerosols. No measurement requirements there. And it just said map land topography, sea ice, and vegetation. Absolutely no numbers there either. And just make a note, there's nothing here about the oceans whatsoever. I noted that, so I focused on that. Nobody else was going to touch it. All right, so on GLASS, they put 3 lasers for redundancy, and they're actually transmitting at 2 frequencies, 1064 for the infrared for the ground, and then for the clouds and aerosols, 512. They would operate at 40 hertz, so 4 times the rate of the MOLA Heritage. The spots on the ground would be a little smaller, about 70 meters. And based on the orbit at 600 kilometers, and the spacecraft moving at 7 kilometers a second, that put the spots about 165 meters apart. To try to get most of the poles, they put it at an inclination of 94 degrees. So you just get a little pole hole at the North Pole. And at the time, people said, well, there's nothing going on at the South Pole. So we can forget that. It was launched into an initial 88-day calibration orbit, so it could repeat a target every 8 days. And then it was designed for a 183-day science orbit. So it would map the Earth very densely for half a year and then repeat that in the second half of the year. Or that was the plan. All right, when you feed the requirements down, that meant detecting ice changes within 1.5 centimeters per year in a 10,000 kilometer square area. For West Antarctica, 0.5 centimeter for East. That boiled down to orbit and attitude errors of less than 5 centimeters for the orbit. An attitude error of 1.5 arc seconds, which is very strict, which gave you a geolocation error within 4.5 meters, so 15 feet. So you should be able to tell if you're at this end of the table or that end of the table. From 600 kilometers up. All right, ISAT did eventually get built and assembled. It was assembled, the spacecraft itself at Ball Aerospace in Colorado. Mission operations were run there out of LASP. And the glass instrument itself was built at NASA Goddard. So I worked at the Center for Space Research across the street under the science team leader, Bob Schutz. And the team was a whole bunch of different government and university folks. It was a good time. All right, it finally got launched, January 13th, 2003. It was Delta II's 99th launch, just for reference. And I guess I'll fast forward. ISAT-2 was launched on the 150th Delta II launch and the final Delta II launch. And it worked. Hooray! There's our first return pulse in red. The transmit is in the light blue there. Yeah, we hit something on the ground. It's not quite a 70 meter circle diameter footprint though. So part of the energy on board the spacecraft was split off into a detector that would try to estimate the shape. That's what this image is, and it's not round. And it wasn't 70, it was over 100 meters. All right, that's okay, it's working, right? Okay, how do we know it's working? All right, I'm gonna jump to calibration at White Sands. So I talked about White Sands a couple times now. This is where we decided to put our calibration site. So if you look, it's that bright white spot right there on Google Earth. It's really bright. Zoom in, flying in. There's that X for the shuttle runway again. So one of the ISAT tracks actually falls very close to that runway. So that, okay, that's not the track, that's another runway there. I'm gonna zoom in. There's that other runway. And there's these other figures there. I don't know if you can see 2 more lines in a circle. Kind of there in the sand. That's about where our experiment was. So right there. Now if you can see some vertical lines there. All right, so that's our primary calibration validation site. All those lines are the wires that we left there. Eventually, over the years, the sand built up and made little mounds along the wires. So that was pretty interesting to see in later Google photos. There were 4 experiments out there, active and passive detector arrays. We tried to take a photo of the laser spot from an aircraft while the spacecraft is flying over. The timing for that was amazing. And then we also did an airborne LiDAR survey and compared to that. In the lower right corner shows the different ISAT tracks. So track 20, ooh. Just for a second, okay. So track 20 was from the 8-day calibration orbit. So we would hit that every 8 days. So that's why we put the test site right there in the middle. From the 183-day repeat, there were 4 tracks nearby, and we'd actually point the spacecraft to the test array. We could alternate or point the spacecraft to hit that site. All right, why did we choose white sands? It's reflective, not quite as white as snow, but pretty reflective. It was restricted access because it's on the White Sands Missile Range. We could leave our equipment there. No one would mess with it. In fact, it's about an hour drive from the gate that we had to get special passes to get through. It's nowhere anyone's gonna mess with it. And it's nearby and less hostile than, say, Greenland or Antarctica. All right, detector array 1. We put up these passive corner cubes exactly like these. These are a couple corner cubes that came off of our experiment. They're only 1.2 centimeters, but we can definitely detect those reflections in the data. We put up different height poles, 1.5, 3, 4.5, and 6 meter poles in a pattern to try to figure out exactly where the footprint was hitting. And then we had active detectors. So this is one of the active detectors. So we have these base plates. They were staked into the ground. I have this tube with the detector electronics here, and little sensor right up top would detect ideally the infrared or the green light and get measured. If it wasn't connected to the computer, the lights would just go on and we could see if it went on, or we could connect these to a base station. I'll go ahead and pass that around that way. And then after a few years in the White Sands environment, the tubes get very scoured by the sand. So I'll pass that one around too. We would go out and set those up every time we were doing a calibration because we didn't want to leave them out.
Tim, do you know how much of the light comes back through the corner reflector? Like how much of it is absorbed in that corner reflector?
From the corner reflector itself?
Yeah, how good are those mirrors?
I'm not sure. Did you get to see one?
No, not yet. But
We'll pass it back, yeah. Yeah, I think it was something like 10 to the 4th, 10 to the 14th photons.
And the fourth.
10 to the 14th photons were sent out and some tiny fraction came back.
Yeah, I got what I'm asking. Yeah, okay. Because I remember something like that for the ranging for the moon. I know it's like a very small fraction of the photons make it back.
Yeah. Yeah, ISAT has a 1 meter diameter, or had a 1 meter diameter telescope to collect the photons. All right, here's the geometry. So it's kind of tilted a little along that ground track. So there were 216 in the secondary denser array, 168 in the primary array. All right, when you put it all together with the corner cube, that's CCR corner cube reflector, those are the locations of all of the detectors that we had out there. Because it was a secure site, we weren't allowed to take photos, except at the very end, we went out with security, and they let us take pictures as long as they looked through the camera before we started. Basically, that was it. We put a camera in the very middle of the array and did a 360. So that's what these are. You can see our car out there, a whole lot of nothing and mountains in the distance. Every once in a while, though, there are telephone poles. You can see in the middle of the middle photo, there are 3 poles. Those are telephone poles. For something that they had done out there at some point.
Yeah, telephone.
Oh, and then later, I looked on, Google Earth, and you could actually see some of the taller poles had fallen down. So that was cool. All right, here's an example of quarter cube detection. So if you just hit flat ground, you're just gonna get basically that red return pulse, just a little bit broadened from what the transmit looks like. But if you get a double peak, that means you've hit something, and these correspond to hitting corner cubes. And by the time difference, you can figure out what height it was and figure out, all right, what row corner cube was it in. Here's an example. We actually hit 2 of them. And I don't remember which cubes, but there was a lot of work looking pulse by pulse at this. All right, let me talk quickly about the airborne photography experiment. We had a Cessna going up, running affectionately called a racetrack pattern, trying to get the timing right. So they would be right over the target when ice sat was over and glass would illuminate that target. We did that multiple times, or at least tried to multiple times. As I said at the beginning, if the shuttle was up, that's their tertiary landing site, we weren't allowed on site, so we couldn't do anything then. If it was cloudy, of course, we wouldn't get a photo. If the camera didn't work, oops, something happened. It actually worked twice out of probably a dozen times trying. Here's the first photo, March 2003. We actually stuck out tiny little LEDs just with a C-cell battery to capture those. And the camera wasn't pointing exactly right, or maybe the spacecraft wasn't pointing right, I forget which. We just got a couple fuzzy footprints in the lower right. And our last photo, which is our second photo, captures some more LEDs. There are some very fuzzy blobs that we correspond to footprints. The streak, the shape of the LEDs actually comes from the motion of the aircraft. So if it yaws a little, rolls a little, you're gonna get those streaks. But we captured them. That worked. We tried something like this at Bonneville Salt Flats with the corner cubes. It was a cloudy day, but someone out there turned their camera upside down, took an exposure, and you could actually see the white streak is the aircraft going by, and then the green spots are the actual green spots from the green laser. So that was a cool photo to get. No pictures of it on the ground, though. Yeah. Based on what we got from the spacecraft in terms of the shape of the footprint, we could map that onto our corner cube array and try to figure out, all right, what part of the footprint actually hit or may have hit a corner cube. We did this multiple times. The white sand is actually the most lasered spot on the Earth by ISAT-1. Anytime we were close and we could point to it, we targeted it. And based on all the experiments, we verified elevation, position, and timing. So hooray, it all worked. We also did airborne LiDAR out there a couple times. March 2003, right at the beginning of the mission, and then halfway through June 2007. We also collected data across the nearby dunes, which are shifting, but we could do a close comparison if the timing was near. And we also did one at Freeman Ranch, which is just near San Marcos, Texas. It's a forested area. We could look at those footprints as well. All right, I mentioned the first laser worked, but there were some issues. I won't read them all here. One of the biggest ones was what's happening with the footprint. It developed this side lobe that actually detached. And then all of a sudden it stopped working. The energy dropped, fell, jumped a couple times, and then just stopped completely. So this was it March 28th, 2003? I don't know if you remember February 1st, 2003? Doug remembers? Yes. Yeah, that's when Columbia accident happened.
We surely remember.
So Columbia was going through their review board, and then a month later, Glass has this anomaly. So they set up a parallel glass anomaly review board, the GARB, as it was called. It obviously was not given the same priority as Columbia, so things took a while longer. But eventually they took out an engineering model, did a, I don't know, this is some high resolution photograph of it. So a lot of the wiring is gold because it doesn't react with anything, which is really nice. It does react, however, with indium. And that's what they found, that the requirements, for whoever manufactured it, didn't tell them not to splatter indium everywhere, but they evidently did. It reacted with the gold, started shorting out the wires. So that was the basic conclusion of the GARB. So then their recommendation was, this is going to probably happen to all the lasers. So how do you prevent this? Number one, operate at a lower temperature. Try to keep things cooler. You're not going to get as much energy, but it may delay this reaction happening. Number two, if we only get another month out of lasers 2 and 3, you want to spread that out. So they're only going to operate, let's say fall and spring, a month at a time. See how long it lasts. All right, so this is a 33-day sub-cycle of the 183 days they originally planned. So now this is the mission ground track. They're going to run these 33 days 2 or 3 times a year. And this is based on the ISAT altitude of 600 kilometers. And then I think at this point, I want to mention ISS and Hubble are below ISAT. What does that mean? Yeah, we don't want to shoot the laser when we're coming close to Hubble or the shuttle or the space station. So we have to turn it off once in a while.
Do you have to worry about anything on the ground, or is it just there's enough scattering in the atmosphere that it's not a problem at that point?
Say again?
Sorry, do you have to worry about anything on the ground?
No, yeah, it's eye safe. Yeah, I've been hit by the laser, the green laser.
Why is it not safe for those orbiting assets?
Just because they're so close. They're only a couple 100 kilometers and there's no atmosphere.
It says, yeah, okay.
Yeah. All right, so these are the laser campaigns that ended up being collected. There were 18 in all. Laser 1, they tried to restart it, didn't restart. They ran laser 2 3 times. And then the energy was dying, so they said, let's go to laser 3. Laser 3 was great. 11 campaigns till that one ended. They said, all right, let's restart laser 2. They actually raised the temperature at that point. They said, well, it's going to fail anyway, but we need more energy. We're going to raise the temperature, and got 2.5 more campaigns out of that. I mentioned the footprint size. So laser 1 went through that transformation where it had a side lobe. Laser 2, again, was not 70 meters around either. It was much larger and oval. Laser 3 was round, but it was only about 50 meters, not 70 meters. So nothing was exactly as designed for the laser.
So what, are you gonna talk more about that? Like why that happened?
Why that happened?
Yeah, like, is it, that they don't know that before it's launched? Or these are things that happen during launch? Things get jiggled and
As far as I know, we don't know why they were that. I don't know what the tolerance was on the 70 meters, but it was very, very different. So in terms of calibration, we've got an instrument that's being turned on and off multiple times a year. It's also getting heated differently by the sun. So the beta prime angle is the angle between the orbit plane and the Earth-Sun line. So when it's in so-called airplane mode, you're very close to close to zero. So it's going in bright sun and then shadow, bright sun and shadow in the top figure there. On the lower one, you're going perpendicular to that, so it's fairly constant. So up top is an image of beta prime angle, that's that curve. Blue is when it's we're in space, what did I say? Red is aircraft mode, that's the orientation of the solar panels. And then blue is spacecraft mode, that's a different orientation. So we're also changing orientation of the solar panels and the instruments as well. And then we've got the laser transmit energy, which is continuously falling. And then the footprint major axis, which is nowhere near 70 meters. So we've got all these different things that we're trying to take account of when we're trying to calibrate it. So oceans to the rescue, I would say. Here's ICESat compared to TOPEX. One of the first pictures I made, it looks like it works. Yay! Very similar. We're getting data over the oceans. That was a big question. If you average, say, the ICESat mean sea surface, or the ICESat elevation minus a mean sea surface, you'll get the anomalies. Here's a picture from laser 1A in the upper left, day by day, what the average sea anomaly is. And it's, where are we at? -7 centimeters or something there. So if you do that campaign by campaign, you get the figure on the upper right. And that just shows changes depending on the processing software we used. But there's definite trends there. Laser 1 had a huge negative bias. The tail end of laser 2 had a positive bias. And then the middle bottom figure, you might not be able to see that. That's the ascending minus descending passes. So essentially when you're going day versus night, there's a huge difference between airplane mode and spacecraft mode for the satellite. So we had to try to account for all of these. A lot of ground-based work has been done on these, what are called inter-campaign biases as well. All right, so I'll just continue showing some of the cool ocean and science stuff. Here's an example from Funafuti, country of Tuvalu. For comparison, there's some JSON footprints. That's a radar altimeter versus different tracks from different campaigns of ICESat. And there's a tide gauge right there at the yellow circle. So I wanted to see, all right, can we compare it to that? Tide gauge comparisons weren't great, but you did see a real good signal going through the lagoon. So when the ICESat data was outside the open ocean, it was kind of rough. Then when we hit very near the coast, the ocean was too calm. We got saturation of the telescope, which is those waveform saturation points. Then we hit land. Tuvalu's mean elevation, or sorry, Funafuti's is about 1 meter above sea level, not very much. And then it's a great calm profile through the ocean. That was really cool to see. We had saturation again, and hit some land, and then back to the open ocean. So it was really giving us finer resolution than we ever had with radar altimetry. I found this tributary of the Amazon, Rio Tapajos, and one of the tracks just happened to go down it. We didn't design it that way. We didn't point there. It just happened to go down it. So on both sides, you're hitting vegetation, but right in the middle, you get very smooth curves along the river, unless there's clouds, and then you get these cloud effects. Lake Pontchartrain, another tide gauge there. That one we actually were able to correlate the tide gauge measurements with ISAT. It's pretty cool. Claudia Carbajal looked at Three Gorges Dam, and was able to see every time they filled the dam, ISAT would measure that corresponding rise, as well as the seasonal cycle. You could look at disaster assessment. So Katrina happened in the middle of the ISAT mission. We looked at the data before and after, and you could definitely see a difference in the highest tree height before versus after. All right, clouds and aerosols. The green laser was the one that primarily looked at clouds and aerosols. One story about that. So there were 8 detectors for the green laser on ISAT. It didn't use the telescope. At some point during construction, ISAT was actually dropped. Whoops. And about half the detectors broke for the green laser. So.
And they didn't fix it.
No, they said it'll still work.
This happens.
But yeah, they got good data like this, good profiles, density of clouds, where they're at. The green laser did fade before the infrared, so they weren't able to get this beyond laser 3, I think. Ice sheet change. I'll just throw this up here to stare at. A lot of people are ice folks here. Dennis Felixson et al. Put this together. We looked at ice change with various different methods, but this is essentially the synthesis of all of that, looking at where everything's changing. So you can stare at that for hours if you want. Later, we actually compared to Grace, trying to get where the density was changing. So it was a good mission. Subglacial lakes, you can actually detect changes of the topography in select regions. Helen Fricker and Ben Smith both did analyses looking at ISAT and finding where all the subglacial lakes are in the Antarctic plumbing.
Laser lakes.
What?
We call them laser lakes, sort of.
Laser lakes?
Because they're not all lakes, and nobody knows really what they're pumping, some of them are lakes, some of them are weird things.
Yeah, they're pumping, they're not very deep usually.
Yeah.
And then sea ice. ISAT was good at hitting the leads between all the sea ice. Sinead Farrell put together an analysis here and showed about a 3 centimeter per year average decline in the sea ice for the first 5 years of ISAT. So I'm not sure where it rebounded, but I know we haven't hit 0 yet. And then global forest measurements. So just like when you're hitting the corner cube on top of a pole, if you're hitting leaves or branches or something above the ground, you're going to get a double return or multiple returns. Mark Samard at JPL put together this map based on all the ISAT data. And it's really cool to see where all the really tall trees are. Above 30 meters, that's a tall tree. All right. Laser status as of May 2010. I found this report as I was digging through things to put this presentation together. So laser 3 stopped firing in October of 2008. They went back to laser 2, as I said, then laser 2 stopped firing in October 2009. The GARB was still active. Anytime we had an issue, we would go to the Glass Anomaly Review Board. They tried to restart the lasers, they didn't. And then they thought, all right, we've got everything working on the spacecraft except the lasers. What can we do with it? So they talked about the Air Force maybe taking it over just for training purposes. Eventually that didn't happen, but they did some other tests. So first was Messenger. And so laser altimeter to map Mercury. So they actually pointed messenger at ISAT and tried to see if they could detect that. They tried in February 2010, and unfortunately, they didn't get a return. But it was a cool test. All right, final days of 2010. February, after that messenger experiment, the spacecraft was retired, no more science. We had always used just the first GPS unit. So they actually turned on the second one and it worked flawlessly. So that was great. But the fuel, it was maneuvered into a lower orbit so that we could have it burn up. See, yeah, 14th of July, final propellant was consumed. A month later, they turned everything off. They said, all right, goodbye. And then it finally re-entered on 30th of August. If anything landed or survived burning up, it would have been probably the primary mirror of the telescope, and that way the Bering Sea. The questions. Doug, you probably got technical ones.
No.
It was just a really cool mission, the number of times that we crossed paths with shuttle or Apollo or things like that. When we used to go out there for the calibration validation at White Sands, sometimes the shuttle pilots were actually doing training flights. So they had an aircraft whose controls were mocked up to work like a space shuttle. So they'd be flying around and we'd see them diving down, buzzing us. Yes, question.
Yeah, so if you hadn't had this issue with like the gold wiring, what was the anticipated kind of life cycle? Like how short, I guess, did it fall?
3-year mission, 5-year goal was what it was. So it essentially lasted 18 months with this. Yeah. We just spread it across 8 years.
Sam, how did it get its name? ISAT.
ISAT, just from the acronym, ice cloud and land elevation. So even though it's called ISAT,
It's pretty fun.
Yeah.
yeah, the I is for ice, C is for cloud, and E is for
The
elevation.
cloud and elevation people must have been kind of. Really de-emphasized. Was Institute involved with Ice Bridge as well after this, or not? The Ice Bridge program that,
Yeah, trying to remember. I think that was mostly the group here working on.
but we were flying for it, our aircraft was part of it. So
Yeah.
It was a massive thing. I just didn't know if you were involved you guys were involved in like architecting it, like.
No, yeah.
Constructing the program.
Yeah, we weren't involved with Ice Bridge. We did roll into ISAT too, though.
Okay.
So we went back out to White Sands, put out more reflectors for an airborne mission that was simulating what ISAT would do, kind of a push broom. So we did work out there. That's when we got to take the photographs when we were out there.
And so what's the difference with what is ISAT, how is ISAT two like, does it share a lot of the components and stuff, or is it totally built and redesigned from scratch?
I would say it's totally redesigned. It's all green, it's photon counting. So you're not sending out huge pulses. You can't see the green anymore.
Okay, all the fun is gone.
Yeah. All the fun's been taken. I mentioned that we could point to different targets. So we pointed to White Sands 50 times. Bob Schutz is the team leader over at CSR, so he could pick anything he wanted. So we targeted Enchanted Rock a few times. We could target the pyramids. Different science team members would have us target different mountains or forests.
Anybody's like house?
Possibly, I don't know. I know we did Kilimanjaro, Forest of Dean in England.
When you point off of Nader, is there a decrease in performance?
There's
Because of scattering?
not that much in terms of the scattering, it's mostly the error in the pointing. Yeah, angle. Yeah, I know we hit Golden Gate Bridge just by accident. Any other questions?
Yeah, I thought you couldn't get the South Pole because you were, yeah, to be right, nadir, but you can be a little off. Like that, but that
Yeah,
area
you
you're talking
try to-
about is what keeps you from, because I thought it was like a hole in the pole.
Yeah. Yeah, they talked about trying to fill the pole hole by going off nadir, but we could only go up to 5 degrees.
So I wouldn't feel much of it.
Yeah,
Yeah, this 2 years ago, we got some coverage that was fulfilled, like, because we were down there for this, and so some of that coverage is, you know, I think pretty unique. Later search, so there's nobody truly got it.
yeah, I said 2 goes to 92 degrees, so there's still
There's still,
a hole there. Well, thank you for having me.
Thank you.